Good afternoon, everybody. One concept that we cover in Chapter 1 that I get a lot of questions about is finding domain. So what I wanted to do is just give you some notes and do a couple of examples for finding domain of a function. Really, when we're looking for domain, what we are looking for is all of the x values that we can plug into the function and get a real number answer back for the y value. So this is all the x values that, when plugged into the function, yield a real number answer. Well, there's an infinite amount of numbers that we could possibly choose for most functions. So the approach we're really going to be taking is looking at our function to decide what we can't use. If we can decide what we can't use, then we're just going to say, well, I can use everything but blank, blank, blank. So there are 3 specific cases that we need to look for. And the first one is if we have a function that contains variables in the denominator. An example of a function that would have a variable in the denominator is f of x equals x plus 2 over x squared minus 9. That function has variables in the denominator, and this is an issue because if the value for that denominator ever comes out to be 0, we would have an undefined y value that would correspond to that x value. And what we're looking for are x values that, when plugged in, yield a real number answer. So we want to avoid any possibilities of the y value being undefined. So when we are given a function that has variables in the denominator, what we want to make sure of is that the denominator will never equal 0. That's the only thing we're concerned with functions that contain variables, is that the denominator will never equal 0. Just as a general case, denominator not equal to 0, and solve. So for this particular function, we want to make sure that x squared minus 9 will never come out to be 0, and we'll solve that by adding the 9 over. So x squared can't equal 9, and then we will square root both sides, and we get x is not allowed to equal positive and negative 3. We can use everything else except for positive and negative 3. Those two values, when plugged back into our original function, would give us a 0 in the denominator, which would give us an undefined y value. And we don't want that. So there's a couple different ways we could write our answer. We could say the domain is all reals except for positive and negative 3. If we wanted interval notation, when we use interval notation, all we want to do is say the stuff we are allowed to use, and we start with the smallest number and work our way all the way up to the largest number. So if we wanted our domain in interval notation, we could go all the way down to negative infinity. We didn't say there's any problems with that. And all the way up to the lowest number we're not allowed to use is negative 3. So everything in between there is fine. And then we could use everything in between negative 3 and positive 3. And then we could use everything bigger than 3. Now, even though I have my numbers written here, negative 3 and positive 3, because I used parentheses in the interval notation, that means we don't actually use that number. So I can use everything less than it, everything in between them, and everything greater than that, which is really the same thing as saying everything except for positive and negative 3. So both of those are acceptable ways to write your answer. Another issue we could come across when calculating domain are even roots. And what I mean by even roots are roots with even indices, such as square roots or fourth roots or 10th roots. Anytime you're taking a root with an even index, it's an even root. And the issue we come across with even roots is we can't take even roots of negative numbers and get a real number answer back. One thing we're going to cover later in this semester is what the square root of -1 is. If you type that into your calculator will say it's an error because it's a non-real number. Well, again, back to the definition for domain, we're looking for x values that when plugged into the function yield a real number answer. So we can't do even roots of negatives. An example of a function that contains an even root is, let's say, the square root of 2x plus 1. To find the domain for this function, the only thing we need to be concerned with is that this stuff inside the square root, which is called the radicand, doesn't ever come out to be negative. We can take the square root of 0, and we can take the square root of all positive numbers, but we can't take square roots of negatives. So we need to make sure that the radicand, which is the expression under the root, is always greater than or equal to 0. We want the radicand to be greater than or equal to 0. So in this case, our radicand is 2x plus 1. I need it to be greater than or equal to 0 in order to get a real number answer back, and then solve. So radicand greater than or equal to 0, and solve. So I will subtract my 1 over, and I get 2x must be greater than or equal to -1, and then I'll divide my 2 over, and I get that x must be greater than or equal to -1/2. So we could leave that as our answer, and that is called inequality notation because I have my answer written as an inequality. Again, what is very common though is to write interval notation. The lowest I could possibly go is -1/2. It says that x must be greater than or equal to -1/2. So the absolute smallest I can go is -1/2. I do use a bracket on that in the interval notation because it says or equals. And it says I can be anything greater than that. So I can go all the way up to positive infinity. And that would be our interval notation for our domain. Those are the two main culprits that we see that require us to throw numbers out of our domain. These two things make it so that we can't plug anything that we want into the function and get a real number answer back. It is possible that there is a combination of those two. So I'm going to write it as a third possibility that we have an even root in our denominator. If we have an even root in the denominator, we have to do kind of a combination of our last two. If we have a denominator, first of all, we can't equal 0 because we're not allowed to divide by 0. And if we have an even root, we need to be positive. So, but with even roots, we could be 0. So if we just combine those two, this case is just going to tell us to throw 0 out of this case. So if we have an even root in a denominator, we would say our radicand must be strictly greater than 0 and solve. So we throw out that option of or equals 0. Because it's in a denominator, we have to throw out the or equals option. So h of x is 2x over the square root of x plus 5. We have an even root in our denominator, and we want to know what the domain is. Well, the only thing that would give us a problem is that even root in the denominator. Now, because it's in the denominator, it's not allowed to equal 0. And because it's under a root, it needs to be positive. And the way that we would write that in a math expression is take our radicand and say it must be strictly greater than 0. And then we need to solve. And to solve that one, all we have to do is subtract our 5 over. And we get x must be greater than -5. And that would be our inequality notation for the domain. Or we could write our interval notation. We've got to be greater than -5. So the smallest I can go is -5, but I can't actually use it, so I do a parenthesis. And we could go anything greater than that all the way up to positive infinity. It's possible we could have other combinations of these two options and have to deal with them simultaneously. And one example of that is f of x is the 4th root of x minus 2 over, let's say, x minus 3. So we have a denominator and we have an even root, but they're two separate pieces. They're not the same thing. So we have to deal with them separately. I know that my radicand must be greater than or equal to 0, and my denominator cannot equal 0. So I've got two things I have to deal with here, and I need to solve both of them and combine them for my answer. So if x minus 2 must be greater than or equal to 0, I can solve that by adding the 2 over, and I get x must be greater than or equal to 2. And if x is minus 3 is not only equal to 0, I can add the 3 over and get that x can't be 3. And I have to write interval notation that combines those. I can use everything bigger than 2 except for 3. And the 2 is included. There is a or equals. So the lowest I can go is 2. And according to this, I can go to infinity. But because of this denominator, I can't use 3. So I'm going to have to stop this at 3. And then I could use everything bigger than 3. And I am using 3 in my interval notation, but because of the parentheses, it means we don't actually use it. So we can do everything in between 2 and 3, including 2, and then everything bigger than 3. For everything else, the domain is all real numbers. And there's no work you need to do whatsoever. In interval notation, all real numbers is negative infinity to positive infinity. So f of x equals the cubed root of x minus 2x plus 9. What we need to ask ourselves is there a denominator? No, there's no denominators, okay? Are there even roots? Nope, there's no even roots. I do have a root here, but it's a cubed root, which is an odd root, so there's no problems with that. There's no denominators, there's no even roots, then there's no problems. Our domain is all real numbers. So the domain here, you can write out all real numbers, or you could use interval notation, say negative infinity to positive infinity. So there's really only two things you're looking for. When you're asked for a domain, you ask yourself those two questions. Is there a denominator? If so, we need to make sure that our denominator does not come out to be 0. The other thing we need to ask ourselves, is there any even roots? If there is, we know we can only take even roots of positive numbers, so we say radicand must be greater than or equal to 0 and solve. It's also possible that we can have a combination of an even root in a denominator or have them separate and have to deal with both cases. But everything else, if there's no even roots, there's no denominators, then there are no numbers we need to exclude, and our domain is all real numbers.